Welcome you all for today's video. Today I am going to explain the reactions of benzene. So first of all I will introduce what are these reactions and basic mechanism for all of the reactions. So stay with me. I am Hasan Kangwarachi. Okay, now I will explain the basics of benzene's reaction, which means electrophilic substitution reactions. We know that benzenes don't prefer electrophilic addition reaction because benzene don't like to lose its strong 5-electron ring. So if it's undergo electrophilic addition reaction, benzene will lose its stability because it will lose its 5 electron, 2 5 electrons, that means 5 bond, that means it will lose its ring structure, fully conjugated ring structure. So benzene doesn't like to go that, so it will undergo only electrophilic substitution reactions. So here carbon-carbon double bond, if we consider normal carbon-carbon double bond, so electrophile will come. We know that the attack is going from 5 bond to electrophile. What is going on here? Here this carbon-carbon double bond contain 2 5 electrons from both carbons. 1 5 electron belongs to this carbon, other one belongs to this carbon. What happened in this reaction? First of all, both of these electrons will goes to one carbon by cleavage in this carbon-carbon 5 bond. This carbon-carbon 5 bond will cleavage towards one carbon, heterolytic cleavage. So heterolytically it will goes to one carbon, and that carbon will get that 2 electrons like this. By getting that 2 electrons, it will get negatively charged. This carbon will be positively charged, and now that 2 lone pair will attack for this electron. That's the basic thing is going on that type of reaction. But normally we draw it as like this. As a general reaction, one step reaction, we will write like this, but the reality is previous thing. This bond will cleavage towards this carbon and that will attack this electrophile. But in general chemistry, we will write this reaction like this. However, this is alkene. This is an alkene. It will readily undergo this type of electrophilic addition reaction. What will happen? This carbon-carbon double bond here, previously it has hydrogen, now this broken and that carbon will attack for this electrophile. This contains this single bond. So previously it had 2 hydrogens. Here also there are 2 hydrogens. Previously carbon had, or any other bonded group, doesn't matter. Here this carbon will get a positive charge after breaking this bond towards this carbon. At that time another nucleophile will come and it will attack for this positive charge. It will stabilize and it will form this type of alkane product. Carbon losses is 5 bonds. So it will become like this. That's the basic thing which is going on in electrophilic addition reaction of alkenes. So what happened here? Instead of 1 5 bond, there are 2 groups attached to this both carbon. One was electrophile and other one was nucleophile. If there is a triple bond, same thing can be happen. At that time both 5 bonds will break and 4 groups will attach to both carbons. So now it is the basic thing in alkenes. So what about benzene? Benzene also contains this type of ring structure, and there are 3 pi bonds. You may argue with me, if benzene contains 3 pi bonds, it also will going on, it will be also will participate for electrophilic addition reactions like alkenes, as I discussed previously. So electrophiles here, you may argue this will broken towards this electrophile and it will form this type of thing with nucleophile. As I discussed previously, please go backward and see that reaction. So you may predict that will happen, but I say no, benzene won't undergo that type of reaction. Why? Benzene is not just a alkene. Why? Here, obvious benzene contain 3 pi bonds, so 3 double bonds. However, this ring is more stable, very stable. Why is that? The strong reason is it is fully conjugated. It will form closed pi-electron ring. What is that? If this 5 bonds conjugated like this, it will produce its other resonance structure like this. Likewise, it will continuously move cyclically. So it will form a ring structure of 5 electrons. If we see from the plane, if you observe this aromatic structure like this, in this plane, it is plane or no? In this plane, in the whiteboard, I will observe it. So I will see it. Its 5 electron cloud will be observed like that, above the ring and below the ring. So it will form closed pi-electron ring. This is more stable, very stable. So benzene is prefer electrophilic substitution, but not prefer electrophilic addition. Why is that? In addition, what is going on in addition? 5 bond will replace from an electrophile and a nucleophile. So if this 1 5 bond losses, and if electrophile and nucleophile bonded to this benzene ring, what happened? The cyclic conjugation structure or closed pi-electron ring will lose from benzene. So here it is stable, but after breaking its 5 bond, it will not fully conjugated, or it will not form closed pi-electron ring. So instead of closed pi-electron ring, it will form this type of half ring. So because here these bonds can form resonance structures. So conjugation is going on between these 4 carbon atoms only. So that will form half ring. Half ring structure is less stable than this closed ring. So if benzene undergo electrophilic addition reaction like that, it will lose its stability. Because of that, benzene will not participate for electrophilic addition reaction, rather than it will undergo electrophilic substitution reaction. What will happen in substitution? In substitution, we know that benzene, it contains 6 hydrogens peripheral bonded to the carbon. In substitution, one of electrophile come and it will substitute instead of this hydrogen, hydrogen will go. What is the product? Nothing will happen to this closed 5-electron ring. Instead of it will substitute electrophile instead of hydrogen. That's the product of electrophilic substitution reaction. So electrophilic substitution is not much effect for the stability of benzene. However, in substitution compounds participate for or bonded to benzene, sometimes it will donate electrons to the our benzene ring, and sometimes it will be withdraw electron from the ring. At that time, sometimes it will activate the ring, and sometimes the substituent group will deactivate the ring. It's different thing. However, forget that thing for just this situation. So in substitution reaction, nothing will happen to the cyclic fully conjugated or closed 5-electron ring of benzene. If it's undergo addition reaction, it will lose its 5 bond and it will not close 5-electron ring. It will be half 5-electron ring. So it will not. So benzene will not undergo that type of electrophilic addition reaction. It will undergo electrophilic substitution reaction. So I will explain the basic things happening in electrophilic substitution reaction, because after this video we have to talk about common benzene rings reaction such as sulfonation, nitration, halogenation, and Friedel-Crafts alkylation and Friedel-Crafts acylation reaction. So there are 5 major reactions, and Gattermann-Koch reaction also. So those are the major reactions in benzene ring. So all of them are going on the method, the mechanism. Now I am going to explain that mechanism. There is a common mechanism. Every reactions of benzene will undergo according to that basic structure of mechanism. So if you carefully listen to me and understand the mechanism, the other reactions will be very easy for you. So please observe this or listen to me very carefully. What happened in electrophilic addition reactions? Sorry, substitution reactions. Here, our benzene is here. Here, electrophile will come. Electrophile means electron deficient group, positively charged. It need electrons. In contrast, benzene, it's electron rich group. Here, benzene acts as a nucleophile because it's contain electrons, 5 electrons, 6 5 electrons. So it is electron rich group, and electrophile is electron deficient group. So what happened here, as I said previously, one of this 5 bond will break towards one of this carbon, and that carbon will get 2 electrons of that bond, broken bond, and that because of that carbon will get a negative charge. That lone pair will attack this electrophile. Always attack goes from a lone pair to a positive charge. Always lone pairs are the attackers to form a bond. Okay. Here, now these 2 reactions, 2 arrows I will draw as 1 arrow. In general chemistry, we draw this as a 1 arrow. So this bond will broken towards this carbon. Okay, you can choose the direction, doesn't matter. I choose this direction. After breaking this bond, this carbon will get negative charge and it will attack electrophile. It will form a bond to electrophile, and here this carbon donate its electrons to this electrophile. Electrophile get electrons. Getting electrons means it get negative charge, and negative charge and positive charge cancel out, and it will be neutralized. and on the other hand upper carbon, it loses a pi bond, so it will get a positive charge. So this positively charged ion is a cation, carbocation. It is known as adenine ion. Or on the other hand, we can call it sigma complex. Why are we calling that sigma complex? Because initially this benzene ring there are 6 carbon hydrogen atoms bonded to this benzene ring. All are sigma bonds. Other than that 6 hydrogens, now new sigma bond formed in between carbon and electrophile. New sigma bond formed. So that's why we call that sigma complex. Okay. In electrophilic substitution reaction, this is the first step. This is the first step. At there, adenine ion is formed. So here it is a positively charged, so somewhat unstable. And in electrophilic substitution reaction, this is the slowest step. Otherwise, on the other hand, it is the rate determining step. So what happened here? This benzene loses one of its pi bond. So now what's happened to the aromaticity? Here we know that benzene is good aromatic compound because it is a planar and ring structure is cyclic. Every carbon is sp2 hybridized and all are fully conjugated form close pi-electron ring, and it obey the Huckel rule. So it is an aromatic compound. What about adenine ion? All of these carbons, including this positive charge carbon, all of these 5 carbons are sp2 hybridized, but this electrophile attached carbon it contains 4 sigma bonds. 4 sigma bond mean it is sp3 hybridized. sp3 hybridized mean its geometry is tetrahedral, not trigonal planar. So sp3 mean it is tetrahedral, that means it is not planar. So this is non-aromatic complex. Oops, what happened? Benzene loses its stability. Look like as a electrophilic addition reaction. It look like a electrophilic addition reaction. In electrophilic addition reactions also it loses its stability. Oh, 1 pi bond. So what happened here? It loses its 1 pi bond and it formed a structure like this, but it contains positive charge. So here in second step, this positive charge, here the electrophile attached group carbon contains a bond with hydrogen. The positive charge will be here. What happens if a nucleophile come and attack this positive charge? If just imagine if a nucleophile come and attack this positive charge, it will form this structure. The electrophile and this here nucleophile. What happened? This is the electrophilic addition reaction product. This is the addition reaction product. We are talking about electrophilic substitution, okay? Don't confuse. So I told you, if that word if a nucleophile attack this positive charge, it will form this type of electrophilic addition product. So it is because of that it loses its pi bond permanently. But here nucleophile don't attack this positive charge. It will attack this hydrogen that bonded to electrophile bearing carbon. Here electrophile bonded to this carbon, the same carbon is bonded to hydrogen, nucleophile will attack that hydrogen, not other hydrogens. Because of this attack, this hydrogen and carbon bond will cleavage towards this carbon. It will get the bond pair of this bond and it will be negatively charged, that will attack for this positive charge. So electron getting by this carbon, so it will be negatively charged, negative charge and positive charge will cancel out and it will be neutralized. Here this carbon hydrogen bond will break towards this carbon. It is getting this lone pair, as I previously said. Because of getting two lone pairs, it will get negatively charged, but now it donate that 2 electrons to this carbon. It will get, because of that donation, it will get again a positive charge. This positive charge and this negative charge cancel out, so it will produce this structure. Again it forms its pi bond. Now electrophile is substituted instead of that hydrogen. Initially in first step it looked like an addition reaction because it loses its pi bond, but after the second step nucleophile attack for that hydrogen and nucleophile combined like this, and benzene ring get its stability again with the substitution product. This is the basic structure of every electrophilic substitution reactions, including halogenation, nitration, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation. Every reaction mechanism is the basic, their basic structure is like this. If you carefully understand this structure, you can easily understand that 5 reactions. Okay. If I draw an energy diagram, for this process, here energy axis, y-axis energy, this is reaction coordination, here our reactants. In first step, what happened? In first step, it will form a carbocation or carbocation. This is the energy of carbocation and this is the energy of transition state. We know that in transition state, what's going on in transition state? Some bonds are breaking, otherwise some bonds are making, present continuous. Some bonds are breaking and some bonds are making during this transition state. Because of that, it is highly unstable than this carbocation. Here you can observe this is a maxima. Maxima means it is a transition state. Minima means it is a intermediate state. So here carbocation formed. Carbocation is much stable than the transition state. Here transition state 1. Okay, this is the first step, formation of carbocation, or otherwise arenium ion or sigma complex. What is going on in second step? We can predict theoretically we can predict 2 products. First one is this electrophilic addition product. Second one is this electrophilic substitution product. So if it is electrophilic addition reaction, I will draw it in my blue pen. Okay. What happened here? In electrophilic addition reaction, it forms electrophilic addition product like this. If it undergoes second pathway, electrophilic substitution reaction, its energy diagram will be like this. What is the meaning of that? Here, the product of electrophilic substitution reaction. So, you can clearly observe that the energy of electrophilic substitution product is low energy. Here, the addition product is much higher energy. It contains much higher energy than the substitution product. That's why we call benzene prefer electrophilic substitution reaction rather than electrophilic addition reaction, because if electrophilic addition reaction happens, the energy of the product is higher than the reactants. So it will absorb here the energy gap of reactants and product of electrophilic addition reaction. So its energy delta G is higher. So this will be a endogonic reaction. So endogonic means production of because if a product contains higher energy than the reactants, it will absorb energy from the environment. That means it is a endogonic reaction. So rather than the electrophilic substitution reaction, its energy much small amount of lower than the reactants. So it will it is a exogonic reaction. It releases energy to the environment. So energy of the product is lower than the reactants. That means it is exogonic reaction. However, in this type of reaction with benzene, the energy of reactant and electrophilic substituted product, the energy is both nearly equal. So energy of reactants and the substitution product is equal, nearly equal. It is somewhat very slightly lower than the reactant. So it is an exogonic reaction. It will release energy. However, we consider it is a nearly equal, both energy of reactant and substitution product. So here, so this electrophilic addition is endogonic reaction. That means it absorbs energy. We have to provide energy. So to happen that this reaction, we have to provide energy. On the other hand, this electrophilic substitution reaction, we don't want to provide energy. It will happen automatically. Okay, that's the thing. So if we consider the energy gap of this first transitional state and the arenium ion, delta G1, the transitional state 2 is the electrophilic addition reaction transitional state. It is the TS2. The energy gap between this TS2 and arenium ion is delta G2, and the energy gap between third transitional state TS2 3, which means electrophilic substitution reaction, energy is delta G3. We can write down the order of decrement of energy. Delta G1 is higher, delta G2 2 is higher than delta G1. So you can see the energy gap of rhenium ion and first transitional state is much higher than other two. That's why it is a we call it as the slowest step or rate determining step. We have to provide more energy to achieve this energy gap. However, other two energies, delta G2 and delta G3, mean the electrophilic addition reactions transitional state and electrophilic substitution reaction transitional state is much lower than that delta G1. However, when we compare these two energies, the electrophilic addition reactions transitional state is highly unstable than the electrophilic substitution reactions transitional state, because this product is the major product and possible product. That's the theory. If you carefully understand, if you understood this theory and this mechanism and this energy diagram, you will understand very easily the sulfonation reaction and nitration reaction and halogenation and Friedel-Crafts alkylation and acylation reaction very easily. So this is the basic sketch of those reactions. So please watch my next video. I will discuss those 5 mechanisms of electrophilic substitution of benzene. Please subscribe my channel and like this video if you understand, and stay with me. Thank you.